So did everything yesterday make sense, or was there anything that that needed some further explanation? Not just the concepts, but also the calculations. You know, when I do the calculations in class, you should repeat the calculations to make sure that you can do them. You know, because if you watch somebody do it, it's different than doing it yourself. So you can watch somebody. You can watch somebody play the piano, but then when you go try it yourself, it's a lot different. Well, you can watch somebody solve a chemistry problem, but when you go and try it yourself, it could be a lot different. And so you just don't want to watch somebody solve a problem, even though you go, oh, you know, I already know how this is done. No, you got to sit there and do it yourself as well. Yeah, we're going to go over some more combined gas law problems here. We haven't finished all the homework here. So I've been doing the blue problems. The blue problems have the companion, you know, the answers in there. So I could do the black problems without the answers in there as well and leave the blues to you. But the thing is, it doesn't really matter. You want to, even if you've seen it once, you know, the thing to do is go back through and then see, do you remember how to solve that particular problem? And so I don't remember. I think we started off, we finished off with number 59. So let's take a look at number 61. A hydrogen cylinder holds gas at 3.67 atmospheres. And so what we'll do is just label these here. So we're going to call that P1. In a laboratory where the temperature is 25 degrees C, so this is going to be T1. And 25 degrees C is room temperature, which is 298 Kelvin. So that's it. To what quantity will the pressure change? Oh, I think we did this. Did I do this one? Yeah, this one we did because I misunderstood the wording here. You know, when they say change, I'm thinking, you know, change is the delta. Delta P in this case, because the pressure is changing. So I was thinking they're asking delta P rather than P2. And so in this, when we look at the answer here, they were asking for P2 rather than the delta P, yeah, which was 3.45. And the delta P was minus 0.22 atmospheres. I think that was it. So we did that one. Let's take a look at number 63 next. A gas storage tank is designed to hold a fixed volume. Okay, so volume doesn't change. So what we can do, if they don't specify it, then we just assume it's constant. And so V equals constant. What that means is, V1 is equal to V2, which is equal to V. And we don't need the number here because this is going to cancel out in the combined gas law. And amount of gas at 1.74 atmospheres. So 1.74 atmospheres we'll call P1. And 27 degrees C, that's going to be T1. And 27 plus 273 is going to give us 300 Kelvin. We need to change it to what we call the absolute temperature scale. I didn't talk that much about it, but in the absolute temperature scale, 0 Kelvin is the absolute coldest temperature you can get, you know. And that we can see from Charles' law. Charles' law is often cited as the reason why that's absolute zero. And so when we look at the volume of gas will contract and contract as the temperature goes down, as it gets colder and colder. And then if we follow this trend line all the way to zero volume, you know, we can't go to negative volume. There's no such thing as a negative volume. And so we can only have a positive volume. We could have a negative volume change, you know, a delta V is different than a V, you know. And for absolute temperature, this is going to be 0 Kelvin. That's the absolute coldest. And so there's no negative Kelvin temperatures. This is why we need the negative. The negative is just because of an arbitrary 0 in the Celsius. On the Celsius scale, this is minus 273 degrees Celsius, or minus 273.15 if you want to be more precise. And that's because the Celsius scale has an arbitrary zero. The arbitrary zero is at 273 Kelvin. And Celsius called this 0 degrees C. This is called 0 degrees C because this is an easily reproducible temperature because of the freezing point of water. The freezing point of water is one of the physical properties of water. Water being a pure substance, its physical property doesn't change. And so that's a consistent temperature that's easy to reach. Reaching this temperature is not so easy, you know. It's very difficult to get to this temperature. In fact, it's not possible on currently, but can get very close to this temperature, very, very close to 0 Kelvin. In fact, liquid helium, it's easy to get 4 Kelvin. 4 Kelvin is the boiling point of helium. So you can liquefy helium, and then as it boils, it maintains a constant temperature of 4 Kelvin. So, all right. So we need to convert it to Kelvin. Otherwise, we have to use the offset formula, as I mentioned before, and I don't want to use the offset formula. To prevent excessive pressure due to overheating, the tank is fitted with a relief valve that opens at 2.0 atmospheres. And so this will be P2. To what temperature, okay, so this is T2, must the gas rise in order to open the valve? And so we're going to use a combined gas law, P1 V1 over, in Chem 1A, it would look like this, N1 T1, which is equal to P2 V2 over N2 T2. And then we cancel out whatever doesn't change. So V doesn't change. And then it's a fixed amount of gas. So we aren't adding gas or removing gas. N, remember, is the amount of gas in units of moles. And so we end up with this equation, and then we're going to solve for P2. P2 is equal to, multiply both sides by T2. I like to keep the ratios like this. So here, we can see what happens to the temperature. If T2 is bigger, that is, the temperature goes up, then the pressure increases. If T2 is smaller, that is, the temperature goes down, and this is a fraction, then the the pressure decreases. So this is the fraction, the change, you know, what we can see is T over 1. And so we can intuitively see, you know, as temperature increases, pressure goes up. And then just plug everything in here. And so when we do that, we can just look at the answer here. We just want to make sure we get the setup correct, and the rest is punching in the numbers. So this is how you can do a lot of questions quickly, you know, just see, okay. So, oops, did I get that wrong? P, not T. We're not solving for P2, we're solving for T2, sorry. And so, and also quickly see if we make a mistake like that. Solving for T2. So I'll get the pressure fraction. This is called the temperature fraction. The pressure fraction, okay, if I solve for T2, T2's down here, so I want to bring it up, and then I'll get P2, and then bring P1 down, and then bring T1 up, I mean, like that. And so T2 is going to equal P2 over P1. So this is the pressure fraction times T1. So let's see what happens to the pressure. The pressure is going up or down. Okay, the pressure is going from 1.7 atmospheres to 2 atmospheres. So the pressure is going up. That means this is going to be greater than 1. That means the temperature is going to go up. If the pressure goes down, then the temperature's got to go down because this is going to be a fraction less than 1. So this is what we call the pressure fraction. This will be the temperature fraction. And so this is why I write it like this. The book also wrote it like this. This is the pressure fraction here. You can see T2, excuse me, I keep getting it mixed up, but P2 over P1 here. And then you can see, so here, yes, the temperature is going to go up to 345 Kelvin. Well, 345 Kelvin, what's that in Celsius? So we've got to take 345 minus 273, that gives us 72 degrees Celsius. So if this warms up to 72 degrees Celsius, then it's going to hit 2 atmospheres. Okay, let's move on here. Clear that. Okay, we go to number 65 here. If 1.62 cubic meters of air, okay, so we're going to call that V1. So V1 at 12 degrees C, so that's T1. 12 plus 273 is going to give us 285 Kelvin. 738 torr, that's P1, is compressed into a 0.140 cubic meter tank. And so this will be V2, and the temperature is raised to 28 degrees C. 28 degrees C is going to be T2. So 28 plus 273 is going to give us, what would that give us? 301, correct? 273, 301 Kelvin. And then 14.7 psi. This is going to be P2. Okay, so what they're asking is what pressure in psi. So first off, the units aren't the same. This isn't psi, this isn't torr. So we're going to have to convert this. Now the conversion is this. This is one of the ones that you should know. Well, actually, 14.7 is special. And so you may, I didn't ask you to memorize that in particular, but if we're at 738 torr, then we're just going to use dimensional analysis to figure out what the pressure is in psi. And the different ways we could do it. I could do it the long way, which I'll do here, and that is there's 760 torr. A torr and a millimeter of mercury are the same thing in 1 atmosphere, ATM. And then there are 14.70 psi per atmosphere. And so that'll tell us how many psi we have. So I'm going to grab my calculator here. Do that. So I break it up, you know, your book is going to combine those two conversion factors, but I break it up because I want repetition. It helps me better memorize the conversion factors if I always write them in the same way. And so even though it might take me more steps to do it, that way I don't have to remember too many different things because I don't want to memorize too many different things. I want to try to keep the memorization to a minimum. That's 14.7. There are definitely things that you're going to have to memorize. You know, it's like learning a new language. You know, if you want to learn a new language and you're anti-memorization, you might say, you know, I don't need to learn any vocabulary or do anything like that because I can always Google it, you know, or Google Translate it. But you aren't going to be fluent, and you aren't going to be fluent in the jargon of chemistry if you always have to Google everything because you don't want to memorize anything. And so this is well, how many sig figs? We're only allowed 3 sig figs here. How many sig figs are in this conversion factor here? 1 atmosphere is equivalent to 760 torr. How many sig figs is that? Infinite. This is infinite. How about this one? 14.7. 4. This one should be 4. That last 0 should be significant. And so this should be 4 sig figs here. This might be by definition. I need to check that. And so we're allowed 3 sig figs here. I'll just carry 1 extra. I'm going to carry 1 extra because this isn't the end of our calculation. We're only allowed 1 rounding step, so I don't want to prematurely round this to 14.3 yet. I'm going to round the final answer at the end. And so this is going to be PSI here. So we're less than 1 atmosphere, or less than 14.7 PSI. This is 1 atmosphere. Okay, so we'll show on the gauge. Now this is very tricky because they're asking about gauge pressure. And we were talking about gauge pressure versus absolute pressure. And so we have to think, are we dealing with gauge pressure? Or are we dealing with absolute pressure? That is, this one seems to be absolute pressure here. And so we need to, remember we have to add little descriptors here so that we don't get mixed up. It says 1.62 cubic meters of air at 12 degrees C and 738 torr. That's got to be absolute pressure. And so this is PSI A here, absolute. Well, they're saying the external pressure is 14.7. Oops, this is a little bit different. And the temperature is raised while the external pressure, this is not the P2, sorry, this is not P2. I need to read it more carefully. This is the external pressure. This is P barometric or P atmospheric. This is P atmosphere, which equals P barometric, which is just 1 atmosphere pressure that particular day. And so what pressure and PSI will show on the gauge. Okay, so what we're going to do is we're just going to do this in terms of absolute pressure and then convert it into gauge pressure next. And so and as far as the combined gas law, we got P1, B1 over N1, T1 is equal to P2, B2 over N2, T2. This is the complete combined gas law. In Chem 4, they decided not to give you any problems where gas is leaking out of the container or extra gas is forced in the container. And so this is why the number or the amount of gas doesn't change. And so we can cancel that out. Here, what else doesn't change? Okay, what else doesn't change is, okay, the volume changed, the temperature changed. And so we have to leave it like this. And so we've got to find out is P2. You know, what is P2? Here, that's what we need to do. Okay, so let's solve this for P2. Solving this for P2, we got P2 is equal to, I'm going to do this in terms of fractions. It's going to be P2 is equal to V1 divided by V2. So this fraction has 1 on top, 2 on the bottom. Okay, so that's the volume fraction. Okay, then I'm going to look at the temperature fraction. Temperature is going to have T2 on top and T1 on the bottom. And then multiplied by P1. So let's see what each fraction does. If the volume increases, let's say V2 is bigger, then this is a fraction less than 1. And therefore, the pressure is going to decrease. So as the volume increases, the pressure should decrease. That makes sense. If the temperature increases, so T2 is bigger than T1, then the temperature fraction is greater than 1, which means the pressure is going to increase. So at higher temperatures, pressure increases. At bigger volumes, the pressure decreases, which makes sense. So the fractions look correct here. All right, then we just plug in the numbers. And so in this case, V1 is 1.62 cubic meters. 1.62 cubic meters. Now the units, it doesn't matter what the units are, they just have to cancel. It's going to be compressed. So the volume's actually shrinking. So if the volume shrinks 0.14, then the pressure should increase. So volume shrinks, pressure increases. Makes sense. 0.140 cubic meters. So cubic meters cancel out cubic meters. Here. And then let's see what's happening with the temperature fraction. So when we look at the temperature, T2, which we calculated here, is 301 Kelvin. So T2 is 301 Kelvin. Here we have to use Kelvin. For the volume fraction, we could use any volume, doesn't matter. But if we don't use Kelvin, then we have to use that other equation I had written on the slide yesterday. And we don't want to use that other equation, although your book does use it. And it's not that complicated, but this is 285 Kelvin here. And so what's happening with the temperature? The temperature is increasing, 285 to 301, therefore the pressure should increase. And so both of these result in larger pressures, both fractions. And so the pressure was 738 torr absolute, or 14.27. This is 14.27 PSI. This is PSI A, absolute. I assume you guys know A and G from yesterday because nobody had any questions on it. So we're going to continue with this. Let's delete this stuff here. If our tank had this, if our tank had this as gauge, if our tank had this as absolute pressure here, then let's see, yeah, an O raised to temperature. Oops, what am I doing here? P, I'm supposed to be multiplying it, not equals. And so let me change that here. This is supposed to be times P1. And so this is P1. And so P2 is equal to what? So doing this, 1.62 divided by 0.14 times 301 divided by 285 times 14.27 equals. And so the pressure comes out to 175.39. I'm carrying extra digits here. I don't want to round yet. PSI A. So that's the absolute pressure. But the thing is, this pressure, if this were in a tank and this was reading PSI A, so let's put a pressure gauge here on the tank. The pressure gauge is reading 175.39 PSI A. Then I open the valve here and let the air leak out. And so as I let the air leak out, will this tank go down to 0 PSI A? Let me ask you that. If I let all the air leak out of this tank, will the pressure drop all the way down to 0 PSI A? Yes or no? Yes, Kazner? Anybody else? Actually, no. Let's do this. Let's see. Actually, no, wouldn't it be the same as the pressure outside the tank? Exactly, Kazra, you're right. You know, this is not going to go down all the way to 0. 0 would indicate there's no gas in here. What's going to happen is there's an opposing force here. What is the opposing force? The opposing force is the external pressure, you know, the external air pressure. And so what we have here is there's pressure inside the tank pushing the air out. At the same time, there's air outside here trying to push its way into the tank. And so this is the atmosphere. Remember, we live at the bottom of an ocean of air. And this ocean of air is going to try to push its way into the tank. But it's not going to be successful because who's going to win? Well, who's going to win is who's ever stronger. And so outside we have 14.7 pounds trying to push its way inside here. And inside the tank, we have 175 pounds trying to force its way out. And so what's going to happen is the compressed air is going to be forced out until the two pressures equal. And so when do the two pressures equal? When the two pressures equal, well, nothing's happening with the atmospheric pressure. That's going to stay at 14.7 PSI A. However, inside this tank, it's going to stop bleeding out or leaking out when the gauge pressure hits. Let me change it back to this color here. When the gauge pressure hits 14.7 PSI. So when we have 14.7 psi A inside the tank here, and 14.7 psi of air outside the tank, then there's no longer a dominant, it's not being forced one way or the other. Now, if this actually went to 0 psi, then there's nothing inside here. And so of course the atmosphere is going to force its way in here. Does that make sense? Okay, good. And so that's psia. And so really, we aren't going to get this last bit of air that's left in here. This last bit of air, the only way we can get this last bit of air in here is to hook it up to a vacuum and then suck it out. But, that's really hard to do. It's like, okay, take a aluminum can, and when you finish, let's say you're drinking a soda in an aluminum can, and when you finish that soda, is that can empty? No, that can is not empty. Well, it's empty of soda, but what's that can full of? The can is full of air. Now I want you to suck the air out of that can. So hold it up to your mouth and suck as hard as you can until the can collapses into nothing. Is that easy to do? No, it's not easy to do. And therefore, what we do here is we just set the gauge to 0. Because the only way we can get rid of that last bit of air is to suck it out. And so we're going to call this, for all purposes, 0. And so this is going to be PSIG. 0 PSIG. That means if you want to get any more gas out of this, you're going to have to suck it out. You're not going to get any more gas by, normally here, there's so much gas in here. It's just going to be forced out of there with, at 175 PSI, it's just being forced out of there. There's pretty high pressure. And so what we need to know is this. Well, we had 175.39 PSI-A. What would that read in PSI-G? Okay, so if we're at 0 PSI-G, we're at 14.7 PSI-A. So what we have to do is we have to add 14.7. And so now what we want to do is we want to go to 175.39 PSI-A. Well, what's that going to be in PSI-G? And so in PSI-G, we got to add that last little bit, that we can't suck out of there. So it's going to be 175.39 plus 14.7, which gives us 190.09. And so this is actually 190.09 PSIG. Oops, did I get that right? Wait a minute. So if it's, well, no, I got to subtract. I want backwards, sorry. I'm not going to be able to extract all 175 PSI. I'm going to come out 14.7 PSI short because I don't want to suck it out of the tank. So I can't use all 175.3. So I got it backwards. 175.39 minus the 14.7 I can't get out of there because it's stuck inside the tank. And so that means I can only use 160.69 PSI out of that. Because once I use all this, 160.69, that's going to leave 14.7 PSI in the tank. And so the tank will be filled with just 1 atmosphere of air. Okay, so the answer is going to be, well, we're allowed how many sig figs? It looks like we're allowed 3 sig figs, so it's going to be 161 PSIG. So 161 PSIG. Okay, this is the tank initially before I drain it. And so they aren't asking about draining it. They just want the tank initially. And so the absolute pressure is 175, but I can't use 14.7 pounds of that. Therefore, I'm only going to get 161 worth of PSI out of that tank. And so let's take a look at how they solved that problem here. And so they calculated the absolute, but they did it in torr. I did it in PSI. And then they converted the torr into PSI. So this is what we call round off air, I think. Let me see, unless I made a mistake. 285. No, don't think so. It looks like they're rounding off heavily here. Yeah. I got 161. What you're going to see is you're going to see slight differences, you know, whether you round or you don't round. But I should double check my calculation because it's still 2 psi off. And so I'll do my calculation again. It's always good to do if you're off. 1.62 divided by 0.14 times 301, 301 divided by 285. Times 14.27. 7838 torr. 7838 torr. Yeah. Wait a minute. Oh, there it is. Yeah, times 738. They just write it differently than I write it. Yeah, they rounded. That's 9.019. So it's going to be off a little bit. Don't do this. Don't do intermediate round off. You know, this is not the final step of the calculation. Each time you round it off, you introduce a little bit of round off error. And so what you do is you carry all the digits in your calculator, 9.019. 13, you know, I just leave all the digits in the calculator times 10 to the third, and then use that in this calculation, and then round it off at the very end, because you can see we're off a bit, 175 absolute versus 174 absolute. Okay. All right, let's go on to the next problem here. 67. The compression ratio in an automobile engine is the ratio, even though we're going through all these problems here, you should go through them yourself and try and, you know, make sure you can do them yourself. You know, you just don't want to be a spectator. Oh, I see that, I see that, I see that. Again, you want to do these yourself if you have time. The compression ratio in an automobile engine is the ratio of the gas pressure at the end of the compression stroke to the pressure at the beginning. It's also the volume too. This is a pressure ratio. You can also do the volume ratio, like 11 to 1, you know, 11 volume to 1. In fact, that's often the case. They don't usually talk in terms of pressure. They usually talk in volume. Assume that compression occurs at constant temperature. It doesn't. You know, the temperature increases, but then you can wait until things cool down. The total volume of a cylinder in an automobile is 350 cubic centimeters. And the displacement, the reduction in volume during the compression stroke is 309 cubic centimeters. What is the compression ratio in that engine? Okay, so let's take a look at this one. And so this is going to be V1. V1 here. Those are doing V2. Well, what about the temperature? What's the temperature? Well, this is constant temperature, so the temperature doesn't change. However, the pressure does change. But where's my P1? You know, where's my P1? And so you might go, if I don't have a P1, I can't solve this. Well, no, you know, what you do is you don't give up. If you don't have a variable, what you do is you assume. There are two choices. When a variable is not given, in science, the two choices are to assume a variable. And so if somebody doesn't give you a variable, then you say, okay, let's assume we're starting at normal pressure, atmospheric pressure, 1 atmosphere. So we assume 1 atmosphere, therefore we can calculate a number. And so number 1, we assume 1. Or number 2, we solve this for an equation, solve for equation. And the equation is going to have P1. And so we solve this for an equation that has P1 in there so that we can see what happens to it. And so what we're going to do is we're going to figure out what is P2. Well, let's calculate what P2 is based on P1. And so this is common this is common in science, but this totally throws off students. You know, students are expecting to have all the numbers. And they aren't expecting to have to assume a number or solve for an equation. And so this is why number 67 is an advanced problem, even though it doesn't. The advanced part is what do you do for P? Well, we know P1 V1 over T1. I'll just do this. N1 T1 is equal to P2 V2 over N2 T2. Okay, and these are a combination of laws. When we throw in N, that's what we call Avogadro's law. And there was a video I was supposed to put in there, but I forgot to put it in. N cancels, N doesn't change, temperature doesn't change. So we just got this scenario here. And so what we're going to do is we're going to solve for P2. P2 is equal to V1 over V2, the volume fraction, times P1. And so here it's going to be 350 over 309. 350 over 309 times P1. The units cancel, cubic centimeters and cubic centimeters. And so there are two ways I can deal with this. One, I can go ahead and assume a pressure. Let's put in 1 atmosphere there. And then this would be the P2 here. Or two, I can solve it for an equation. I'm going to solve it for an equation in this particular case. I can put any pressure I have in as your beginning pressure here. It's probably just going to be 1 atmosphere anyway. But this is one. I can also solve it for an equation like this, too. The pressure fraction is equal to 350 over 309. Okay, and so, well, what is 350 divided by 309? So 350 divided by 309 is equal to 1.132. And so what happens is the pressure goes up from 1 to 1.132. And so this is the pressure fraction here, just 1.132. We're allowed 3 sig figs, so it's just 1.13. And so the pressure fraction goes up by 1.13. And so it gets compressed a little bit and the pressure goes up. So let's take a look at what their answer is here. Oh, okay. This one, volume at the start, volume at the end. Oops. Okay, so this is good because I didn't waste too much time, but I ended up getting this totally wrong because of the volume. I didn't read this question carefully enough, so let me redo this because I did this completely wrong. And so I labeled this, you know, and this is what you have to be careful with because misreading this. The total volume of a cylinder in an automobile is 350 cubic centimeters, and the displacement, the reduction in volume during the compression stroke. Okay, this is a delta V. This is not a V. I have to be careful because in the earlier problem, I was assuming they were talking about a delta P, but they were talking about a P instead. And so we have to be careful here because in this case, this is not a V, this is a delta V. And so that's why I didn't get it. This is not V2, this is the delta V. So this is V1, then the reduction in volume, I lose this much volume. And so if I started off with 350 cubic centimeters, I lost 309 cubic centimeters, which gives me the V2. And so that's going to be 350 minus 309. Well, 350 minus 309 is 41 cubic centimeters. So actually V2 is equal to 41 cubic centimeters. So this is where I screwed up here. I have to be careful how they read it. In the last problem I read it, well, it was very confusing. I didn't like how they worded it because it made it sound like that was a delta P, but they were talking about a P. In this problem, it was clearly a delta V. I just didn't even think they were going to ask a delta V because all these questions had me trained you know, V1, V2, P1, P2, T1, T2. And then all of a sudden they throw in a little wrench. This is the advantage. This is the advantage of doing all the problems. The advantage of doing all the problems is you can see the little tricks and the twists they throw in there. You know, oh, that was tricky because that didn't follow every other single problem I did. And so this is why the people who look at all this, every single homework problem have an edge. They have an edge above. And people are always trying to get that edge, you know, because, for example, a lot of people want to go to medical school. Well, you're going to have an edge to go to medical school. You don't want just an A, you know, to get for medical school, an A is not enough. So to hit 90, for a lot of classes for me, 90% is enough. But for a lot of people, they don't want 90, they want the top score. Or if not the top score, they want to be in the top 3 in the class, you know. And so how do they do that? Well, like I said, a lot of people look at this. And so when you see this, this is like, if you only study one tree and you're only used to doing one type of problem, okay, I'm used to doing it this way all the time because this is the only tree I've studied in the forest. So I know this tree and I know it very well. You're missing all the other trees in the forest. And so all of a sudden we see another little tree here in the forest that threw me for a loop. Maybe it might not have thrown you for a loop, but you know, it threw me for a loop because I was used to a pattern. And so this bucked the pattern. This was the very last problem. And so my fraction is different. My fraction was 350 over 309. It's actually 350 over 41, which gives me an 8.5, 8.5 to 1, you know, volume, or 8.5 to 1 pressure, because volume and pressure are directly proportional. And so this is P2 over P1 here. Okay. All right, there's one more problem that I wanted to do, and this one more problem I wanted to do was the STP. This book has way too many STP problems for my taste. That's why I skipped all of them. It had way too many STP. And STP, let me tell you something. What actually, this is going to be in the next section. I memorized STP. Not only did I memorize STP, I memorized what the volume of a gas is at STP. 1 mole, you know, that's the quantity, a mole of gas is, it was related to how many molecules are in there. 1 mole of gas has what we call an Avogadro's numbers worth of molecules, which is 6.022 times 10 to the 23rd molecules. Has a volume of 22.4 liters. I memorized that when I was taking, I memorized that in high school, and then I memorized it again. I forgot it, and then I memorized it again when I was taking the equivalent of Chem 4. And in all my decades of chemistry, how many times have I used it? 0. So it was a waste of memory. I can't forget it though. It's like burned in my memory. I want to make room for other things, but I can't. That's a useless piece of memorization. So you might use it. I was looked in some gas catalogs where they have things at STP. So you might use it. So I should do at least 1 problem with STP. And so let's take a look at 1 problem with STP, but this book has like 20 problems with STP. And so, let's see, where were those STP problems? Here it is. STP, 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 STP. That's too many STP problems. So let's do 1 STP problem, and you should know what STP is probably. I mean, and so let's try maybe the last one might be the hardest. This one. A container with a volume of 56.2 liters. Okay, so 56.2 liters. I'm going to call that V1. It's at STP. Well, STP, what does that stand for? That stands for standard temperature and pressure. So if we're at STP, then T1 is 0 degrees C, which is 273 Kelvin. And P1 is, okay, they're using the European, the metric one, which is 1 bar. 1 bar and 1 atmosphere are almost the same. You know, bar is a little bit smaller. And so if you recall, 1 atmosphere is equal to 1.01 bar. This is 3 sig figs. Or if you want it exact, this one's not too hard to remember, 101.325. This is exact, or infinite sig figs. But you can see it's almost the same, you know, 1 versus 101. So not a huge difference. And so normal pressure is about 1 bar. And rather than using torr or millimeters of mercury, they use millibar. You know, there are 1,000 millibars in 1 bar. The gas is compressed to 23.7 liters. So this is V2. And 2.09 bar, which is P2. And so let's go ahead and do that. So we got P1 V1 over N1, which is the amount. T1 is equal to P2 V2 over N2 T2. The number of moles doesn't change, or the amount. What else doesn't change? Actually, everything else changes. Okay, so what we want to do is we want to solve for T2. So I'm going to solve for T2. So T2, we'll bring it to the left and then move everything to the right. And so it's going to be P2 divided by P1, pressure fraction, and then move the temperature. And so this is going to be T1 divided by T2. And let's make sure I got the fractions correct. Times T1. Make sure the fractions are correct. If the pressure increases, temperature increases. That makes sense. If the temperature, oh, well, this should be volume, sorry. No, this should be volume here. I made a mistake. So let's look at this volume here. The volume fraction is going to be V2 over V1. So if the volume increases, the temperature must have increased. So that makes sense there. So the fractions look correct. Let's just plug it in. And so let's check the answer here. So here's the pressure fraction. You know, 2.09 bar was our final, 1 bar is our initial. Here's the volume fraction, 27.3 liters for final, 56.2 initial, and then the initial temperature, 273 Kelvin. Okay, that gives us 241 Kelvin, and then convert that into Celsius. It gives us minus 32 degrees Celsius. Okay. So that's an STP problem. STP problem is just, it's easy because they're telling you, but how often do you work at 0 degrees C? Well, maybe you do, you know, depends if you work in a freezer or something, you know, then you do. Or if you freeze it, or you aren't going to freeze the gas, but you know, when we say freeze, it's freezing water. Water freezes at 0 degrees C, but a gas doesn't. Unless the gas is steam, steam would be frozen 0 degrees C. All right, so those are some types of questions you'll encounter, and so we looked at a variety. I skipped some of these, you know, like these multiple choice ones, you know, and true and false ones that you can go through yourself quite quickly, you know. These are good for conceptual checks, and they don't take very long to do. All right, are there any questions on chapter 4 before we leave it? Chapter 4. Okay, no. Let's go on to chapter 5. These drawings here. All right. Can we do one more at STP? Yeah, we could do one more at STP. That's fine. Let's do this one, the first one here. Or let's see which one's interesting. This might be interesting. Let's try this one here. 49. Look at 49. An experiment is designed to yield 44.5 milliliters of oxygen measured at STP. It's a yield. When I think of yield, I think in terms of our chemical equation. In our chemical equation, we have the reactants on the left, and then we have this little arrow, and then we have products on the right. This arrow, people say not arrow. They don't call that a forward arrow. They say yields. And so reactants yields products. And so this is designed to yield this. Well, if it's designed to yield that, then I call that V2 because that's what we should yield. And then STP, well, that means T2 is going to be 273 Kelvin or 0 degrees Celsius, and P2 is going to be 1 bar. And so this is where we want to be at the end, at the products. So what must it have been before? Okay, so what they're going to do is they're going to take this gas and then make it conform to STP. And so if the actual temperature, so this is going to be T1. T1, 273 plus 28 is 301 Kelvin. So 301 Kelvin. And then the pressure is this many bars. So P1 is 0.894 bar. So what they're doing is they're taking this gas here and then they're forcing it to be at STP. So what's going to happen here to make it conform to STP, you know? And so maybe the gas has to go smaller. Maybe the gas has to get bigger. I don't know. We'll find out. Actually, we can think it through as well, but just figure it out. So how do we do that? So we use the combined gas law. So from now on, I don't care what Charles' law, Boyle's law, all the other laws are. I just care about the combined gas law because the combined gas law is the only one you need to know up to now. And the Avogadro's law. I'll show you this in a minute in the video. So, yeah, so we aren't leaking or adding any gas in there, so that doesn't change. And so we want V1, you know, what volume would it be? This is O2, oxygen, so we're looking for V1. So solving for V1 is here. So V1 is equal to P2 over P1. We'll move everything to the right. And then it's going to equal T1 over T2, T1 over T2 times V2. Sorry. So if the pressure goes up, I think I screwed this up. If the pressure goes up, then the volume goes up. That doesn't make sense. If the pressure goes up, the volume should go down. So I think I screwed that up. Let me think about that. And then if the temperature goes up, the volume should go. Oh, I see. I screwed this up. Do you see this is backwards? If the pressure goes up, the volume should shrink. If the temperature goes up, the volume should expand. I got this backwards. So let me do that. I need not everything on the right. I need everything on the left. Oh, wait a minute. No, I'm solving for V1, sorry. So if I solve for V1, I'm solving for the initial, and then what happens after that. And so I am solving for this. It's just this problem is backwards. This is what we want at the end, but we are trying to figure out what we started at the beginning. So this is backwards from all the other problems. And so this is another benefit for seeing all the fours. You know, if you see all the fours, then you see, oh, this one is different than all the others, you know. It's like, you know, I don't know if you watch like Sesame Street, you know, or something like that. One of these things is not like the other. Well, this one's not like the other. And as well as number 67, that last problem was not like the other. And so, which is what you'd expect, you know, so the more variety you see, the better, ultimately. So it's too bad these were all at STP, but, you know, maybe there's some valid ones in here. This is why you look at all of them to see if they come out as expected or different. And so anyway, I'm solving for V1, so that's actually correct. So V1 is equal to, and we are going backwards here, so that's why. And so it's equal to P2 over P1, and then T1 over T2, T1 over T2, because we're going backwards. But don't worry about it. If it doesn't make sense, just do the algebra. You know, if you do the algebra, you'll be safe, times V2. All right, so let's just plug in the numbers and then see. Well, that's our setup. So we already figured out all the P1s and everything else. And so let's see how the book did it to save time. See how the book. Obviously, you want to do this yourself too. So we have 44.5, which is V2. And then we have the 301 on the top, which is T1 over T2, 273. And then we have P2, 1 bar, and then P1. And so we have it set up correctly. We just need to plug in the numbers and do it. And so you should plug in the numbers and do it. But after you do a bunch of these, then you can kind of streamline things as well. All right, is that enough for the STPs and the combined gas law? Okay, let's move on to next chapter. What time is it now? Let me see something. It's about time for a break. Let me do something for this. Okay, let's go ahead. Let's take a break for 15, and then we'll come back after that break. Okay, sorry. I'm going to get back started. Had some issues with people not being able to access the Zoom still. I know this class isn't for everyone, so if you know of anybody who's dropped, the drop deadline is tomorrow, and so they'll have to process it. Did anyone just come in after the break? Just trying to add the class? No? All right. Okay, let's continue. We're going on to chapter 5 next, but before I do that, I just wanted to show one thing. And that is the combined gas law combines multiple laws, not just Charles and Boyle's law, but there are more. And so let me show you what I'm talking about here. Just back over. restart the recording. Oh, actually, I never stopped the recording, so there's a big gap in the recording. Sorry. And so we'll just continue here. One of the laws that's incorporated in there is called the well, it's called Avogadro's when it's done like this, volume and moles, but this is volume and pressure. I mean, quantity. Quantity is N, you know, how much gas you have. And usually units of N are moles. And so how many moles of gas we have and pressure. So let's check out this video here.
If the number of gas molecules in a container is doubled with no change in the temperature or volume, the number of collisions between gas molecules and the container walls doubles, which translates into a doubling of pressure.
So here, if you double the amount of gas in here, so you insert more gas, and we double the amount, then obviously you're going to get twice as many collisions. Twice as many collisions is going to result in twice as much pressure. Now, that's for a fixed container. If the container is flexible, you know, rather than doubling the pressure, the container volume expands like a balloon, then you double the volume rather than doubling the pressure, you know. Okay, so that was the last bit. I forgot to incorporate that into the PowerPoints, but that was the last video I wanted to show for that. Let's go back to the PowerPoint. So we're doing chapter 5 next. Chapter 5 deals with atomic theory. We talked about atoms already, you know. We talked about Dalton's atomic theory. Where did Dalton's atomic theory come from? You know, the theory is ultimately what we want, because the theory, you know, like I try to minimize how much memorization I have to do. I try to memorize it, minimize the amount of memorization that I have to do. And with the theory, you should be able to make predictions, you know, without having to actually observe things experimentally, right? And so the theories are a result of the scientific method. So it's probably a good idea to go back through it, you know, and see the basis of a theory. And so the theory starts off with what? Observation. Yeah, that's correct. Tuesday's our first exam. I'll talk more. I should talk more about it later today. So we start off with observation. So what was the observation that led to Dalton's atomic theory? Anybody recall? This should be pretty quick recall because we had already talked about it and you should probably have reviewed it maybe at least once or twice. The law of multiple proportions is the law, but I want the actual observations. What were the actual observations that led to Dalton's atomic theory? Gold is not infinitely divisible. Prove that. Did somebody actually prove that and observe that in Dalton's time? In Dalton's time, did somebody take a piece of gold and try to divide it into smaller and smaller pieces? What they found out is they could divide it into smaller and smaller pieces until they couldn't even see it. So based on macroscopic observations, you know, with your eyes, you would think gold is infinitely divisible, because gold, they can get it into the thinnest of thin, you know, gold leaf and even thinner pieces of gold, which barely have any gold, you know, to them. And so that wasn't an observation, because they were not able to infinitely divide or at least attempt to infinitely divisible. I mean, it carried on. You would think it would be infinitely divisible based on their observations. Yeah, it was burning wood, and what else? What about burning wood? What observation specifically about burning wood? Or what observation about any other thing? What was the observation? This goes back to Le Chatelier. You know, what did Le Chatelier observe in his experiments, in his reactions? The phosphorus, you know, the P4 burning, and the mercury. Remember, this is like training, you know, this is like you're training I don't know what you're into. I mean, if you're into basketball, you'd be training for basketball. You don't want to be the slowest person on the court, right? You want to train for speed. You want to train for accuracy and shooting baskets and that type of stuff. Well, this is the same thing. You don't want to be the slowest person on the test. You're going to be at the bottom of the curve. A lot of classes are curved, you know, and you definitely do not want to be at the bottom of the curve, because the bottom of the curve is DNF. And so you've got to train yourself. Right. The wood lost weight and the phosphorus gained weight. Was that the observation that led to it? Well, that's what most people's observations were, but Le Chatelier took very exacting observations. And what did he observe? So, you know, so basically, if you're training for, you know, and then the big game is the test. The big game is coming up. The test is coming up on Tuesday. Have you been practicing? Yeah, Lavoisier. What did he observe? He didn't, wood lost weight, phosphorus gained weight, but that's not all. He was very exacting in his observations. What did he observe? So the big game is coming up. Have you been practicing enough? The weight did not change. There it is. Okay, Carlos, you got it. But that took way too long. You guys, if you're training, you know, for time tests, you gotta brush up on your speed, your recall speed, because not in this class, but many classes, speed, you're tested on speed as well. So what Lavoisier observed was the mass before reaction and the mass after reaction was the same. And the law doesn't, you just don't take one observation. You have to take lots and lots of observations. And if you see a recurring pattern, and this recurring pattern doesn't have very many exceptions, you know, we see it over and over. It's not a law yet. It's just a pattern. And we want to make sure that pattern is, you know, recurring, or the trend is recurring. Pattern or trend with minimal exceptions, then we can call it the law. And so the law didn't come first. The law came based on these reproducible patterns and consistently reproducible patterns, and that's what we call a law. You know, if it has lots of exceptions, we don't call it a law. What do we call it? A rule. Good, good. That's the kind of recall you want. You know, that's good. That's fast. You know. And then you know it, you know. Well, it's not, again, this is not a game of, there's a memorization, but you got to get the basics, you know. You get the basics memorized, then you can do the advanced stuff, you know. It makes the advanced stuff easier. If you're still struggling learning the basics, there's no way you're going to get the advanced problems. And so here we go, observation, pattern, trend, law to hypothesis. There are different hypotheses for this, you know, phlogiston, whatever. You know, but the phlogiston, is incorrect. Actually, phlogiston wasn't this. Phlogiston was, you know, the mass did change, and what lost was the phlogiston, and I guess phlogiston must have weighed something too. But eventually we get to a theory, and ultimately the theory is what we want. But theory is hard work, you know. It's like Newton. Have you heard of the theory of gravity? You know, the theory of gravity. Where did the theory of gravity come from? What observation led to the theory of gravity? You know, this is Isaac Newton, the apple falling, right? The apple falling on Newton's head, that's a classic, that's the observation. It led to a pattern and trend, led to Newton's laws, which eventually led to, you know, gravity out here, Newton's laws of motion, that kind of stuff. And so, you know, coming up with a hypothesis sometimes isn't so easy. You know, you got to have lots and lots of observations to do that, to come up with a reasonable hypothesis. But anyway, Dalton came up with the first meaningful atomic theory. Other people hypothesized this as well, but Dalton put it all together. This is Dalton here in this picture, and these are the elements that, this is from Dalton's manuscript, his book. And these are the basic tenets of Dalton's atomic theory. An element is made up of atoms. All atoms of a given element are identical. This is wrong here. This is, they aren't all identical. They're all identical in one sense, but we'll see that there's something called isotopes that Dalton didn't know about. And so this theory has been modified to modern atomic theory. Isotopes have different mass. And so when we look at all atoms of carbon, some of the atoms weigh more than the others. We'll talk about it, but chemically they behave similar. Physically, they're a little bit different because of their weights. Atoms cannot be created or destroyed or created. This actually is wrong because of nuclear chem. This is true in chemistry. In chemistry, we never, because what are the rules of chemistry? Or what's the force of nature that we look at in chemistry? Well, the first law of thermodynamics is something we're very worried about. We were very concerned about in chemistry, the first law of thermodynamics. First law of thermodynamics comes from observations as well. First law of thermodynamics came from observations of energy, we saw, just like mass, But nuclear chemists play by a different set of rules, right, than chemists. Chemists are interested in what force of nature. Gravity, electrical, okay. Yes. Then nuclear chemists, they don't care about that. So for chemists, atoms this is good for chemistry, but not for nuclear chemistry. All atoms of any given element have the same properties, including mass. This is wrong. This is wrong because of isotopes. They have the same properties, chemical properties. And so they have the same chemical properties. But they have slightly different physical properties because some weigh more than others. So same chemical properties, but the physical properties are going to differ a little bit because the mass is different. And so like one carbon atom looks just the same as the other carbon atom, but one is just slightly heavier than the other carbon atom here. And so but they both behave just like carbon, the chemical properties, but one's a little heavier, so it's going to have a little more density to it and other things. So some of the physical properties are different. Same chemical properties, physical properties are slightly different. Physical props are slightly different. In modern atomic theory. Atoms of different elements may combine in a ratio of small whole numbers. We call this the law of multiple proportions, law of multiple proportions. This is one of the successes of Dalton's atomic theory. And so an example would be like carbon monoxide, CO, carbon monoxide, or CO2. The color scheme is wrong, unfortunately, sorry. This might be like CO2. We usually use black for carbon and red for oxygen. So this is why it's throwing me off. Blue is usually for nitrogen. But that's a rule, that's not set in stone, and people violate rules all the time, but people don't violate laws all the time. Okay. Let's move on. Here's a rearrangement of atoms in a chemical reaction. So this is visualizing atoms using an electron microscopy, scanning. I think this is scanning tunneling or scanning electron microscope. You can see the resolution is pretty poor, but this is actually visualizing, chemical change, in the rearrangement of atoms. What exactly is that chemical change? It didn't say, but it just switched, you know, they increased the temperature and things rearranged. And so this is new compound versus this one here. All right, so what we want to know about atoms is, you know, certain atoms behave differently than others. In other words, the properties of hydrogen are different than the properties of helium. And so if we want to understand properties, then we better understand what? If we want to better understand properties, then we better understand, what's the title of this slide? Or maybe it's not the recall. I'm not sure how many people are actually here. Okay. Composition and structure. That's right. Yeah. Natasha, I did take roll. I just took roll based on the participants here, but I probably should I need to do another roll because tomorrow is the drop deadline. And let's see, I have some no-shows here. Make sure. Okay, all right, thanks. Thanks for letting me know you're here. Is anybody here trying to add the class? I don't understand something, you know, a lot of people still have not been able to join Piazza for some reason. So I'm receiving a lot of emails. Yeah, it's not going to work through Canvas, so you have to click the link in the invitation I sent out. Yeah, the link in the email, right? I think the problem is they're trying to join it through Canvas, and so still have not been able to join it yet. Let me, in fact, there's an email right now, so let me just do this really quick and try to get this guy to, into the class, the Zoom. So, click Zoom link. All right. So we're back here now. We want the composition and structure. So if we want to understand why is a hydrogen atom different than a helium atom, then we got to know what is a hydrogen atom made up of, what is a helium made up of, and how is its structure. And so this is an atom. The atom is going to be just a spherical thing here. And this is the basic structure. In the center of the atom is something that's a very tiny thing called the nucleus. And the atom itself is a lot bigger. The atom is approximately 10 to the minus 10 meters. We have, let me tell you a different unit here. 10 to the minus 10 is meters, is defined as the angstrom. And so 10 to the minus 10 meters is defined as, well, let's just do this. 1 times 10 to the minus 10 meters is 1 angstrom. 1 angstrom. An angstrom is 10 to the minus 10 meters. So this is approximately 1 angstrom. 1 angstrom here. And so atoms range from about 1 to 6 angstroms. And so this is, you know, approximately 1 to 6 angstroms. Or approximately, let's say, atom radii, yeah. Well, no, let's say atoms. Maybe around 1 to 6 angstroms, but angstroms, you know, the problem with angstroms is, let's say it's 1.31. A lot of people don't like writing decimal points here, and so if we have 1.31 angstroms, that's equal to 1.31 times 10 to the minus 10 meters, or that's equal to 131 picometers. 131 picometers means I can write without a decimal point. And so writing it without a decimal point is convenient, it's handy. Rather than saying 1.31, we say 131. 131 picometers is 131 times 10 to the minus 12 meters. And so picometers is the most common the given unit for atoms. For atoms, atoms range from about 100 to about 600 picometers. This is a useful number. You know, you don't want to memorize a whole bunch of numbers, but one of them you might want to memorize is this. You know, how big are atoms? About 100 to 600 picometers. If we look at the nucleus is about 10,000 times smaller. 10,000 times smaller than the atom. And so there's lots of analogies. One analogy is like this. If the nucleus is a ping pong ball, so let's say you blew up the nucleus to a ping pong ball or scaled it up, then the atom would be like a football field. And so if you take a football field and throw a ping pong ball or golf ball right in the center of that, that would give you some perspective on the dimensions. So this is not to scale here, because if this were a football field, you know, a ping pong ball wouldn't be that big, or a golf ball wouldn't be, it'd just be a tiny dot. And so this nucleus is too big for the scale here. But it's just a cartoon, so it's all right. Inside then, well, what are atoms made up of? Okay, so this is kind of the structure of the atom here. But the composition is, it's made up of electrons, which we call E minus. And it's made of protons, which are called P plus, and neutrons, which are N0. And so I put the charges on here. Electrons have a negative charge, or 1 minus charge, or -1 charge. Protons are +1 charge. Sometimes they write the magnitude and then the charge after. Sometimes we write the charge and then the magnitude after. It depends. There's a rule regarding this, and I'll talk about that later. And the neutrons are 0 charged, so they're neutral. And so we got a bunch of protons crammed in here. Does the nucleus look like this? No, this is just a cartoon of the nucleus. You know, what exactly does the nucleus look like is still being sorted out. You know, but the atom looks like this, and the electrons are out here. You know, we got the electrons out here. The nucleus, well, if electrical forces are the most important in chemistry, then what's holding the nucleus together? Because like charges repel. So each of these red things is positively charged. If each of these red things is positively charged and the neutral neutrons are there, then what's holding this together? What's holding this together are nuclear forces. And as part of that, you know, some of the mass is converted into the nuclear binding energy, which we talked about. And so some people say the neutrons are the glue that holds the nucleus together. And so some people say that the neutron is the glue that holds it together. But we don't mess, you know, with the nucleus. The nucleus doesn't change. The atoms just get rearranged in chemical reactions. That's it. So this is kind of the basic structure. We're going to dig deeper into the structure. You know, this is still very not detailed enough to figure out why things are different in terms of property. A little bit of history here, you know, the discovered. So we'll talk about the discovery of the electron by J.J. Thomson. This is J.J. Thomson. And we'll talk about the discovery of this. This is called the nuclear atom model. What observations led to the nuclear atom model? Or, you know, this model here, what observations led to it? There are two hypotheses about this. You know, we have the nuclear atom versus the plum pudding model. The plum pudding models where it was more homogeneous, you know. In the plum pudding model, everything was kind of distributed evenly. in this atom. You know, the protons were dispersed through there, the electrons and neutrons. But it turned out the plum pudding failed because there are some observations that couldn't be explained by the plum pudding, that couldn't be described by the plum pudding model. The proton was discovered by Rutherford, and the neutron was discovered by Chadwick, but you don't need to know this here. It's not that important. Let's move on here. These two experiments are really important. J.J. Thomson, this guy here, and Ernest Rutherford, this guy here. These are two pivotal. You know, J.D. Thomson's electron, Rutherford is the nuclear model of the atom. Let's move on. So how did J.D. Thomson do this? And so the electron, again, was J.J. Thomson. Oh, okay, that didn't work. Let's go here. J.J. Thomson. Is there a P there? No, I don't remember. I'll have to go back and look. No P. All right, thank you. J.J. Thomson. J.J. Thomson, the way he discovered the electron was by using a CRT. CRT stands for cathode ray. Cathode ray tube. Cathode ray tube. Or a Crookes. This is also called a Crookes tube, etc. Cathode ray tubes used to be used in televisions and that type of stuff. You know. So, what is a cathode ray tube? Cathode ray generated this mysterious cathode rays. You know, cathode rays turned out to be electrons, a beam of electrons. So cathode rays equals a beam of electrons. And so let's take a look at this video here. There's no audio in this. Okay, let me back it up here. This is a cathode ray tube. On the cathode ray tube, you see this wire going in here, and this is called an electrode, just a piece of metal. So I got a chunk of metal there. So we have an electrode, a chunk of metal here, and then we have an electrode here. This thing is there's a slit. You see there's a narrow slit here, right here. And so what happens is we generate the cathode rays, which are electrons. And the cathode rays are dispersed here, like this. And they're being pulled towards this one. This one's positively charged electrode. And this turns out to be a negatively charged electrode. So we're generating electrons over here, and they're being pulled over here. As electrons get pulled, most of them are going to smash into this wall here, but there's a tiny slit here, and what's going to happen is only electrons that are lined with the slit will pass through, so we're going to get a beam of electrons like this. The beam of electrons are going to be pulled straight towards this electrode here. So we should see the electrons like that. Can you see electrons with your eyes? Are they visible with your, no. You can't see them. And so how do we see electrons? How we see electrons is this backing screen here. This backing screen curves into the path of the electrons. And so a lot of the electrons are going to hit this backing screen. This backing screen has what we call a phosphorescent coating. Phosphorescent coating. And this phosphorescent coating glows when electrons strike it. It glows green. And so as electrons hit that, it'll go green so that we can see the beam of electrons here. So let's see. Okay, come on. There. Well, this is a different one. Shoot. I was looking for videos. We have that. The one I just showed you, we have that one in there, but but I didn't go to school to get a video of it. So I was looking for a video, suitable video on YouTube. So I just found this one yesterday. Okay, here's the electrode, except this one, you see the slit here and then the piece of metal here, it looks like they didn't bypass it. It looks like there are no electrical leads here. They could have bypassed this by putting electric leads here. So these are dead here, these metals, this piece of metal. And so over here, this one's negative. So over here, this is negative. And so we're generating electrons here, and the electrons are going to hit this wall here. And just the ones that are aligned with the slit will pass through here. So we'll get the electrons passing through. And so as electrons pass through here, they're going to hit the phosphorescent coating. Boom, it hits it. And then it generates this light so that we can see the beam. The beam of electrons are going across here, and eventually they'll hit this piece of metal here, which is positive. We have to make this very positive and this very negative in order for this to happen. So what we need is something called like 5,000 volts of electricity to do this. And the gas in here, inside here, we have a low pressure gas. If this is room temperature, room pressure, if this is 1 bar, then we need more than 5,000 volts. We need like 20,000 volts. And so what they do is they lower the pressure to make it easier for electrons to travel there and to generate the electrons themselves. Okay, so one thing is they played with the beam. And so let's see how they're going to play with the beam here. Okay, shoot. Yeah, hit the pause key. One, I should, okay. Now, what is that? That's a magnet there. So this is just a magnet, little magnet. Watch what the magnet does to the beam. Do you see? The magnet deflects the electrons. Actually, it's deflecting them towards the magnet. If you flip, I wish they did this. If you flip the magnet upside down, it deflects it one way. And so if you have the magnet in one orientation, North Pole, South Pole, it pulls it. If you flip it the opposite orientation, it flips it down. And so what they discovered is this. They discovered that this beam consisted of negatively charged particles because of the way they interact with the magnet. Not only that, if you put a piece of metal in here, the metal would acquire negative charge in the path of the beam, you know, as the electrons are hitting the metal, you know. And so the cathode rays turned out to be negatively charged particles. Now, the cathode rays were originating over here. And so it looks like they have a piece of metal here, but it doesn't matter what piece of metal it is. And so what they did was they changed the metal here. They went, you could use aluminum, you could use steel, you could use iron, you could do whatever, platinum. So they changed the metal to any metal they can think of, and they put it here that would work. And they generated the same cathode rays. So it appeared that the cathode rays were present in all metals. And so from this, they figured that electrons must be a fundamental part of all matter because they just extended it from metals to other pieces of matter. It has to be something that conducts electricity here, otherwise it doesn't work in this. But that was the discovery of the electron, that they changed the metal here and they still generated the same cathode rays, and these are tiny electrically charged particles. Go on. This is Rutherford's experiment here. Rutherford determined the nuclear atom model, and Rutherford's nuclear atom model here, as we see, what Rutherford did was he shot a narrow beam of fast-moving alpha particles. Alpha particles are positively charged particles. Alpha particles, inside here is a radioactive. Radioactive atoms are inside here. And the radioactive atoms have unstable nucleus, and chunks of the nucleus break off. These chunks could be alpha particles. Those alpha particles get shot out. Some energy, there's some energy released there. And so these are positively charged particles. In fact, they're positive 2 particles. The alpha particles we represent like this, He2+. He is helium. They're actually helium. 2+. They get shot out of here. Most of the alpha particles went actually straight through, undeflected. Most of these, they're being shot. A beam of positively charged alpha particles is directed at a very thin gold film. A fluorescent screen, this is like, on the CRT, a fluorescent screen coated with zinc sulfide detects the particles passing through the deflected foil. Most alpha particles go straight through. Some of the alpha particles are deflected at high angles. Some alpha particles are deflected back. They're deflected back because you got a positive charge particle hitting a positive charged nucleus. A positive, they repel each other, boom. You get shot back. Most of them go right through because the nucleus is only a tiny, remember it's the golf ball in the football field. So if you're shooting alpha particles, how often are you going to hit a nucleus? Not very often. Most of them are going to go through the football field. Very few are going to hit the little golf ball in the center of the football field. Some might pass close by. If it passes close by, then it gets deflected at a small angle here. Okay, the only way that this could be true is if all the positive charge were concentrated into a tiny volume. And that tiny volume is what we call the nucleus. And so this was the definitive experiment which sealed the demise of the plum pudding model. The plum pudding model wouldn't have resulted in a pattern like this. And so that hypothesis was dropped. This hypothesis succeeded, and this is our modern day picture, basically. Our modern day picture is a little bit more detailed than this, but this is it. All right, let's move on here. I'll show a little video. We can show this.
In the Rutherford experiment, gold foil was bombarded by a beam of positively charged alpha particles. Most passed straight through. Some, however, deflected at large angles, with a few coming almost straight back. The particles were deflected by a high positive charge in a very small volume, the atomic nucleus.
So let's summarize the nuclear atom model here. One, every atom contains an extremely small, extremely dense nucleus. It's extremely dense. I didn't talk about the mass, did I? Let me go back and look at the mass. Shoot. It doesn't really talk. Most of the mass of the atom is in the nucleus here. In the mass, what we use for mass is something called the U, because the grams, it's so small. So we need a much smaller unit. And so the mass of the neutron is about 1 U. The mass of a proton is about 1 U. The mass of an electron is about 2,000 times lighter here. And so it's 0.005 U. Is that 2,000 times about lighter? And so what is 1 divided by 2,000? 1 divided by 2,000, just roughly. 5 times 10 to the minus 4. Oops, that's wrong. 5 times 10 to the minus 4. This is 5 times 10 to the minus 3. Sorry. It's 0.0005 U. So electron doesn't weigh anything. So outside the nucleus, there's not much weight, because electrons are very light. Electrons are light. Protons and neutrons are a lot heavier, and protons and neutrons are. And so this is why they call it extremely massive or dense, is because most of the mass, in fact, nearly all the mass of the atom is concentrated into the size of a golf ball on a football field. So, you know, if you're thinking about the weight of the atom, it's concentrated in an extremely tiny, tiny volume. So nearly all mass of the atom is in here. And we were talking about densities earlier, you know, and I talked about the density. What was the most dense thing that I talked about? And what was its approximate density? Was it water? What was the density of water? Three sig figs is too much. You know, for water, water changes a little bit. So sig figs is a little bit precise, too precise, because the density of water changes slightly with temperature. And so we'd see it in 3 sig figs. So usually you memorize it to 2 sig figs. What's the density of water to 2 sig figs? Yeah, okay, 1.0. You're thinking, this is so much information to memorize, but it isn't. You memorize a little bit at a time. Every day you're reading through your notes, you know, 1, 2, 3 times a day, if you can do it. You know, at this point, it's easy to do because your notes are so short. By the end of the semester, it's a little harder because it gets longer, you know. But when you're doing this and you're reading it over and over again, then it's easy. You know, if somebody kept telling you over and over and over again, density of water 1.0, 1.0, 1.0, you know, it's like driving to school or work or something, or riding your bike to your friend's house or something like that. You know, it's automatic. But anyway, going to this, what was the most dense thing that we had talked about? So 1.0 was water. On the low end were gases. Gases were 1,000 times less. It wasn't mercury. Mercury was about 13 and a half, something like that. What was the most dense species we talked about? Was it lead? Was lead the most dense species? No, lead wasn't. Lead has half the density of gold. Gold is about twice as dense as lead. Yeah, gold was. And what was the density of gold? Roughly, you know, to 1 or 2 sig figs. Just give it to me to 1 sig fig. Yeah, it was like 19, 20. Not 219 though. Yeah, 19. Yeah. 19 might be hard to remember, so you just remember about 20. Okay, got it, Kazra. But, you know, Kazra, 219, you know, we have an experiment where we determine the density of water, you know, in the laboratory. And you know how many times people wrote the density of water is 420 grams per milliliter? 420, there's a reason why it came out 420, but we'll talk about it later. Lots. I mean, lots being maybe three people in the class wrote that the density of water is 420 grams per milliliter. And you think, you know, if you're a scientist, you think they're nuts, you know, they're crazy. There's something mentally wrong. They should be put in some institution, because water having a density of 420 is ridiculous, right? But to them, it was, yeah, it's what the calculator punched out, or it's what I got, you know, 420. And so why do you bother memorizing certain numbers? You memorize them so you don't put yourself in a foolish situation where you're quoting some ridiculous number and everybody else is secretly laughing at you because your number is so out there that you're out of touch with reality. And so we memorize certain reference points so that we know what the numbers mean. Now that was an extreme example. People aren't going to be laughing at you. They'll probably feel sorry for you. But the thing is, you memorize certain numbers, and of course we can't memorize all the numbers, but we want to memorize certain numbers so that we know, you know, what the perspective is. And so this is it. You know, I memorized this. You know, how big are atoms? 100 to 600 picometers. Do I memorize how big the nucleus is? No, I memorize that the nucleus is about 10,000 times smaller. And so the nucleus is about 10,000 times smaller. Okay, let's right now, let me go on a break here. I'm sorry, we'll take a little bit earlier break. Let's take a break for 15. I got to take care of something right now, okay? So I'm gonna stop for a break.